Say you're a high school senior and are really excited about technology and realize that coding is a great skill to have that can open up many doors for you. After you've made your decision to major in computer science, what's in store for you? Find out next on Hello World. This is Hello World, a podcast about the fun, exciting, and fascinating world of computer science, software engineering, and technology. Hello World is a production of the Orchidware Studios LLC in San Diego, California. Welcome to the second episode of Hello World. I'm your host, Richard Bernardino, and I hope you're having a great day. So, what's it like to study computer science? We live in a world where software is now a major component of our everyday lives, whether we notice it or not. So having an appreciation for software is a great thing to have nowadays. There is no better way to appreciate what software can do than to build software, be it websites, desktop applications, or mobile phone apps. However, to gain a deep appreciation for what computers can do and what's in store for the future, having knowledge of computer science is the best way to get that understanding. In this and the next episode, we'll talk about what it's like to be a computer science student. We'll talk about the classes and the types of questions that you'll be able to answer and ask after you complete your major courses. Computer science is a multifaceted discipline. On one side, you have the application of computer science that allows you to create computer software that we can all use. However, computer science also has some fascinating theoretical questions that it tries to answer. We'll be talking about these theoretical questions as well. To guide our discussion, we'll talk about the core sequence of classes that computer science majors usually take as an undergraduate. We'll be discussing common courses that are universal to computer science curriculums. We'll give you a sampling of the core courses that a computer science student will need to know in order to get an internship or software engineering job in industry. So, if you go on the web and find the computer science department of your favorite university, you'll find courses that I'll mention. What I'll mention are what you'll typically find. After taking the basic computer science courses, then the sky's the limit on what you can do with that knowledge. That's why I love computer science so much. It allows you to take ideas and make things that help people in their everyday daily lives. It's a really exhilarating feeling. We'll begin our journey into computer science after these messages. So let's begin the walkthrough. Let's start with the prerequisite courses that you'll need to take. Before you get into your major classes, you'll need some basic math. The more math you can get, the better. While not necessary, understanding the concepts of calculus will give you an advantage in more advanced computer science and engineering courses. Linear algebra is a study of vectors and is very helpful in understanding computer graphics. In the application that I'm building now, which is a video game, the most common math operations are adding, subtracting, and multiplying vectors. Having knowledge about trigonometry is also very helpful. In my video game application, I use trigonometry to calculate distances using trig functions such as sine, cosine, and tangent. I also need to calculate angles at 0, 90, 180, and 270 degrees, so there's not much complex trigonometry involved now. However, future releases will allow the player to move in 360 degrees. That's where the trigonometry gets more involved. So having an understanding of trigonometry and calculus is great to have in your tool belt of knowledge. In computer science, you'll be required to take a class in discrete mathematics, which teaches about logic and the math of discrete sets. Discrete sets are what we experience in computers, where numbers are broken up into finite sets of small ranges, while continuous sets are what we experience in the real world. Discrete math teaches logical operations that are key to programming. The most basic logical operations that you'll use in programming and digital logic design involve the operations AND, OR, NOT, and exclusive OR XOR. It also helps to have some knowledge of latches and flip-flops, which are used for remembering state. In my video game application, I use latches in order to correctly use the buttons on the gamepad. Without using the concepts of latches, the button presses would be detected too many times. However, what is needed is to only detect button presses when the user presses down or releases the button. This is where latches help me solve this problem. You'll have to write mathematical proofs in discrete mathematics courses. For example, how do you prove that a number is odd? How do you prove that a number is even? These are the types of questions you'll face in discrete mathematics. You'll need to take an Intro to Programming course, which will usually expose you to object-oriented programming. Object-oriented programming is a way of programming that facilitates having many developers working on the same project. It divides functionality into small parts so it's easier to understand. In OOP languages, you have the idea of a child class that derives properties from a parent class. By doing this, you increase code reuse, which increases code testability, because you're constantly testing the same code over and over again. So that covers some of the prerequisite courses that you'll face that will give you a head start into your fun and exciting major courses. We'll begin on that journey after the break. After you've completed your basic math, logic, and intro to programming courses and have decided, yes, this is the major for me, what's next? Common courses that you'll encounter are courses in data structures, algorithms, operating systems, automata, computation, computer hardware, and software engineering. A data structures course covers how you hold data in the random access memory or RAM of the computer. We understand that there are databases that store lots of data. Hard drives also store lots of data. However, programmers need to store data in data structures that are fast to search and retrieve data from. It's the idea of proximity to the CPU that's important to realize here. The quickest way for your computer's CPU to get data is from memory. If the data is not in memory, it will go to your hard drive where you may have a database. However, accessing the hard drive is slower than going to RAM. So the more your program can access data from memory, the faster your program will run. This is why it's important to understand data structures. Data structures hold and operate data in memory. Basic data structures include arrays, lists, trees, heaps, and maps, just to name a few. In a data structures class, you will learn how to create these from scratch, and you will gain an appreciation for the complexity and efficiency of algorithms. Having a knowledge of many data structures is like having many tools in your tool belt. When you write applications, you'll need to be able to analyze the problem and select the best tool from your tool belt. Some data structures have fast insertion, while they have slow retrieval, like a linked list. On the other hand, some data structures have slow insertion, while they have fast retrieval, like a sorted list. Why is it important to have so many data structures in our knowledge tool belt? Well, firstly, they're important to understand so that you can efficiently store and retrieve data quickly and efficiently, depending on your application and problem. Different applications will require different data structures. Moreover, if you choose the wrong data structure, your application can appear sluggish and can have lag that users will notice. After learning basic data structures, you'll be able to make engineering decisions that will be best suited for the problems you will face later in your classes and professional work. After these messages, we'll talk about algorithms. After you complete your data structures class, you'll usually take an introductory class on algorithms. What is an algorithm? An algorithm is a systematic sequence of steps that are used to solve a problem. For example, to open a locked door with a key, an algorithm will be to first take the key out of your pocket, next to find the key in your key ring for the door that you need to open. Next, you insert the key into the keyhole. Next, you turn the key to unlock the door. Then you finally open the door. This is a simple real-life example of an algorithm that is based on a simple sequence of steps. Now, if we take the simple real-world example and ask the following question. If there are many keys on the key ring, how do you find the right key to open the door? To solve this question, you might say, well, I look at all the keys on the key ring and I find the key that I remember will open the door. That's how we as humans solve the problem. We are good at looking at a bunch of data, such as all the keys on the key ring, and finding the key that matches the one we remember. However, a computer in the traditional sense is only able to look at a small set of items, usually only two. So a brute force method for a computer to solve this problem is to look at each key on the ring one by one until you find the key that matches the image that you remember. And consider that if the keys are not somehow sorted in any way, you will not be able to do any better than the algorithm we just discussed. However, if you could somehow sort the keys on the keyring in some way, maybe from smallest to largest, then you can do better than the brute force method. By sorting the keys, the method of binary search then becomes possible. We've all played the game where we've had to guess which is the number that someone is thinking of within a given range. For example, if I asked you to think of a number in the range of 1 to 100, you'd probably guess 50. If I told you the number I was thinking of was higher, then you'd next say 75. If I told you that the number I was thinking of was lower, then you'd guess a number around 62. We'd continue with this until you found the number that I was thinking of. This is an example of binary search. Binary means 2. In each step of the binary search algorithm, you're dividing the possible set of answers into two parts, the lower half and the upper half. So, these are the types of issues that you examine in an algorithms class. After the break, we'll continue talking about algorithms. In computer science, algorithms are necessary to give us proven and repeatable steps to solving programming problems in efficient ways. In your Introduction to Algorithms class, you'll study a lot about searching and sorting. In our Guess the Number example we just talked about, that was an example of a searching problem. Let's now consider an example of a sorting problem. Consider the problem of sorting the deck of cards. If you were to shuffle a deck of cards, 52 cards, and then lay the cards out side by side, all 52 of them, how do you sort them efficiently? Take a moment and think about how you would do that. Remember, computers are not humans and will only look at the cards you tell them to look at. So basically, computers can only compare 2 cards at a time. As a side note, in programming, we start counting with the number 0 rather than 1. So the second from the left card is card number 1. One way to sort is called bubble sort, where you start from the 2 leftmost cards, let's call them card 0 and card 1, and sort them, with the higher card being on the right. Then you move to the first and second cards on the left side and sort them. Then you move to the second and third cards on the left side and sort them. And so on and so forth until you get all the way down to the rightmost card. This will then put the highest card into the rightmost slot. You repeat this process starting with the rightmost card and swapping cards until you reach the next to last card on the right. And repeat doing this. At each step, you will have the sorted cards on the right side of your deck. After you do this 52 times, you'll have all the cards sorted from left to right. Give it a try when you have a deck of cards handy. This algorithm is called bubble sort. I guess it's called bubble sort because you're bubbling the cards up from the left side to the right side at each step. Then you may ask, how do we say that this is quote unquote efficient? What does the word efficient mean? In algorithms, you use big O notation to mathematically describe efficiency. In this case, we say that bubble sort is big O of n squared. The n squared part is because bubble sort is a loop within a loop when you look at the code. There's a more rigorous mathematical definition of big O that you'll get in an algorithms class, but for the most part, understanding that bubble sort is big O of n squared is sufficient. But can you do better than that? Sure. There are other algorithms that can sort more quickly. One algorithm is called quicksort. Quicksort is an n log n algorithm. When you look at a graph of n log n and overlay a graph of n squared, you'll see that n squared is larger than n log n most of the time. Thus, we can say mathematically, quicksort runs faster than bubble sort. This is the type of analysis you do in an algorithms class. Typically, you'll implement searching and sorting algorithms from scratch, and then analyze their runtimes. For example, we said that bubble sort has a runtime of n squared. As we mentioned with data structures, the selection of appropriate data structures can have dramatic effect on the user experience of your algorithm. Likewise, the selection of appropriate algorithms can also have an effect on how your users experience your application. An important thing to note is that when we compare algorithms, we only think of large numbers of items to be operated on. Thus, big O is used mainly when thinking about larger data sets. If you're sorting 5 cards, it doesn't matter which algorithm you use, you can use a brute force method and it won't make much more difference than if you use an extremely efficient algorithm. However, if you sort 52 cards, you'll want to start thinking about more efficient ways of doing things. Moreover, if you're sorting 5.2 million cards, you'll definitely want to use efficient data structures and select fast algorithms. Otherwise, your application will be very slow or may not be able to solve the problem within many, many years on the fastest supercomputers in the world. So this wraps up part 1 of our discussion into the experiences of a computer science major in college. In part 2, we'll continue our look at the life of a computer science major. If you have any questions, feel free to reach out on our Twitter feed at @OWSound. This is Richard Bernardino. I thank you for listening. It's now time to put a semicolon on the end of this show. You have been listening to Hello World on OW Sound, a production of the Orchidware Studios LLC in San Diego, California. For more information, visit our website at orchidwarestudios.com.